Welcome to this fourth WIPAC webinar on resilience monitoring in rising mains, featuring Ben Smither of Syrinix and Lorenzo Pompa of Anglian Water. My name is Oliver Griefson of WIPAC, the Water Industry Process Automation and Control Group, and technical lead at ZTech Control Systems. Thanks must go today to Wastewater Education 501 for hosting the platform, and to WET for sponsoring the platform as well. If you like this webinar, please feel free to join the LinkedIn group, Water Industry Process Automation and Control. Subscribe to our YouTube channel and visit our website to subscribe to WIPAC Monthly, the magazine that comes out each month. Thank you and enjoy the webinar. Oliver Griefson. I am the Executive Director of Water Industry Process Automation and Control, and I'm a technical lead at ZTech Control Systems. Welcome to the fourth WIPAC webinar. Today we are lucky to have Ben Smither of Syrinix and Lorenzo Pompa of Anglian Water, and they're going to be talking about resilience monitoring in rising mains. It's a project I think I've seen develop over the past few years, and just from afar, and it's really exciting what they are doing. For those of you who don't know what WIPAC is the Water Industry Process Automation and Control Group. It was set up on LinkedIn about 11 years ago. 9 years ago, sorry. I'm adding some age. And it's grown to about 8,000 members. In the next couple of months, it's going to be set up as a community interest company in the UK. So keep an eye. We do these WIPAC webinars periodically. Normally, I try to get them done about once a month on various subjects. They are recorded and they are put on YouTube afterwards. So today we have Ben Smither of Syrinix and Lorenzo Pompa of Anglian Water, and I'll get them to introduce themselves. So Ben, do you want to introduce yourself?
Oh, thank you, Oliver. So I'm VP Engineering at Syrinix. I've been there for sort of 8 years or so, 7 years, and experience from monitoring and control systems in automotive as well as water. So I've been, since 2012, capturing and analysing pressure transient events occurring in water and wastewater systems, so designing systems and analysis techniques with my colleagues at Syrinix and with sort of engaged customers like Anglian and Lorenzo.
So Lorenzo, do you want to introduce yourself?
Yes. Hello, so I'm Lorenzo Pompa. I'm for Anglian Water, so I work on what we call water recycling, more commonly known as wastewater services. Been working for Anglian for nearly 12 years now, predominantly within the sort of maintenance environment on clean water and wastewater as well. So sort of common themes of what I've been doing is how we look at our asset infrastructure and how we optimize it. And working very, very closely with Syrinix on this project that we're going to present today on how we can visualize rising main pressures and then start to use that data to sort of predict bursts, etc. Work on quite a wide variety of assets across the whole wastewater.
Okay, so I will take us over to the presentation screen and let Ben and Lorenzo take over.
Brilliant, thank you. Right, Oliver, just before we go, I'm getting a slight echo still. Are you able to mute the microphones of the participants?
I'll get them to mute themselves as much as can, and I will mute them as much as I can. It doesn't seem like I have control over everyone, so.
I might turn my volume down a bit. Okay, I'll get going and we'll see how we go. Okay. Well, thank you very much for the introductions. So Syrinix have been monitoring pressure and pressure transients in potable water networks for the last 8 years. And over that time, we've learned a lot about the value of monitoring in water networks. So we found that detailed data leads to more informed decision making and planning in the long term. Gives you faster notifications when operations deviate from the norm. You can get detailed information to help manage ongoing operational issues, and sort of hopefully this leads to reduced operational costs and increased asset life. And more recently, in a world struggling with COVID-19 pandemic, we're starting to see other benefits as well of monitoring, and that's a reduced requirement to perform routine site visits, as you can assess performance remotely more easily in many instances. And when problems do occur, you can go in and hit the ground with a higher level of knowledge, so requiring fewer people to actually go on site to investigate problems. So just getting back to monitoring, since 2016, so in 2016, following on from all of the work with sort of potable water, we started to investigate, along with Anglian, the possibility of monitoring rising mains, so pumped sewers, and investigating the value of monitoring pumped sewers. So I'll hand over now to Lorenzo just to give his view of the start of this project, and then we'll get into some of the detail.
So thanks, Ben. So rising mains traditionally are fed from sort of pumping stations, and we haven't really monitored them in the past. And the reason why we wanted to kick off this project with Syrinix was because we were learning that they were doing some really good stuff with the water side in terms of handling transients and monitoring pressures, and we wanted to see whether there was any way that we could pick up on burst events on rising mains. They serve as a large proportion of some of our severe sort of pollutions that we get, and we wanted to be able to monitor them and get there before the impact got more severe. So we approached Syrinix, and one of our sort of key successes, key measurables that we wanted from the project was, can we, from pressure monitoring data, see if a rising main has burst? And that was one of the key things when we installed a number, when we got 122 pressure monitors out there in the network at the moment at pumping stations. That was the key sort of deliverable from the project. We wanted to put these pressure monitors out, and we wanted to measure the drop in pressure, the increase in pressure, whatever told us that there was a burst on that rising main. The next things that we wanted to really start to learn was, and what we saw from a clean water perspective, was the transient data. So we wanted to understand how our system was performing to make some sort of smart investment decisions. I think one of the key things, and we've had this on lots of sort of seminars, webinars, our assets are getting older. The challenges that we're having across the different amps are a restriction in the funding that we have to replace these assets. So we need to look at different ways in how we can operate them, and that was one of the exploratory stages. Once we started to install these monitors, right, great, we can start picking up on bursts now, but what is this 128 sample a second data actually telling us? And how can we leverage this data to start deferring capital and start installing some smart solutions and relatively cheap solutions on pumping stations in the way we operate them to reduce burst frequencies and increase the life of our assets? On top of all of that as well, and while we were exploring that, and we are continuing to explore that, is how can we improve our operational efficiency? So we started to look at, with the standard 1 minute data, how we can monitor how NRVs are performing. How can we monitor the sort of wear on a pump? How can we monitor the NRV slam, so we can make some quick operational decisions to how our pumping station is performing to stop it failing in the future? So we've been exploring all these sort of key sort of deliverables from the pressure monitoring data, and we've had some great successes that we're going to talk through throughout this project, throughout this presentation. Just go on to the next slide. So I'll talk a little bit around how we did it. So we have installed 124 monitors across our most risky assets. Predominantly the assets were picked by how many bursts we've had on them. Some of it was around the locations of the sites, where the rising main locations were going through sites of sensitive interest. And so there's quite a wide spread on different variety of assets from 2-inch up to the largest I've seen is about 600 mil. So we've got a really good data set from all different types of materials of rising main, all different types of pumps, speeds, pressures, and we've got a really good learning that we've been doing for the last sort of a year and a half, 2 years, and we've accelerated that within that period. And how we did it, and you can see from the pictures here on the bottom left, we on every site, on every rising main, we put an under pressure tapping. We put an 1.5 inch under pressure tapping, separate from any other mechanical piece of instrument or device on site. So we started off as the trials, putting on top of non-return valves, but we separated that. We didn't want them on there because non-return valves are a maintainable piece of kit, and what we were worried about is if we started to maintain that, it could damage the sensor. So we tried to keep it completely separate within the dry well. So we put under pressure tapping, really easy, non-invasive solution, cost-effective way of installing these units. So there's very limited disruption to the network. With these, and what we have learned quite a lot in the last sort of year and a half, was that they are communicating over cellular network. So that we did have various challenges of how we would get antennas out of chambers, how we would try and position them to get the best sort of signal quality, because signal quality affects the battery as well. So those were quite challenging, but we're in a very good place now. We've learned a lot. We know where to position our antennas. We know how to get the best out of the cellular signal. You can also see as well on the bottom left the position in the battery. Predominantly, the 124 are all battery powered on pumping stations. We are moving away from that at the moment into a more permanent power solution. That gives us advantages of increasing our data frequency and increasing the amount of data we bring back from the units. Not every site will be able to do this, but we've been working with Syrinix to sort of leverage that opportunity as well. So in the future, we're going to be installing more of these pressure monitors, but we're going to look at start permanently power. Ben.
Unmute. So in order to start collecting data from these sites, and early in the project, we had to develop a new transducer. The potable water monitor had an internal transducer with a small port, which was likely to clog with the sort of rag and fats, oils and greases in the wastewater. So designed a remote transducer with a large open diaphragm, which is on the under pressure tapping that Lorenzo mentioned, so that we wouldn't get ragging and clogging problems. On the end of a cable, so that we could separate the telemetry device from the transducer if we were in deep chambers where you want the transducer down on the main and the telemetry device up at the top where the cellular signal was. And the other reason for the separation was so that we in future can more easily go for ATEX approvals, so we can introduce some energy limiting device in the cable to produce a transducer that's able to work in a zoned environment, and a telemetry device that can be positioned outside of the explosive environment. But we haven't been pushed to do that yet. In terms of the data feeds from the device is monitoring pressure 128 times a second all the time. So you have this continual feed of very high sample rate pressure data. And then we have algorithms on the device looking for pressure transients, so sharp changes in pressure, and sending those. So on a rising main, and that's typically pump starts and stops. And also, at the moment for Lorenzo, we're sending summary data 4 times a day, and that summary data is the min, mean, and max pressure seen in every minute of the day. So if you've got 128 samples a second for a minute, and we're reporting the maximum pressure seen, the minimum, and the average of all of those samples. For us, in terms of battery life and cellular, the big cost is sending this raw stream of 128 samples a second. So if we sent it all, we'd reduce the battery life and use a lot of data. But the optimum position is actually to send the summary data, which gives you most of the detail, and the high sample rate data just for the events. So moving on to this. So in terms of the deployments, we found that most rising mains you can monitor from a single point, as shown in this slide. We've got typically you're after the last non-return valve in the pump station. You want to see the pressure in the rising main. You don't want to see the pump side of the non-return valve. And looking at that point, you can see the delivery pressure from the pumps when they're running. When the pumps are off and the non-return valves are closed, you see the static head in the rising main from the high point. And you also see any transients occurring on the rising main side when the pumps start and stop. Sometimes on longer mains, especially sort of undulating ones, you'll want another monitoring point partway along. These ones where you get trapped air and air coming in through the air relief valves. Right, as Lorenzo was saying, the mounting method's been sort of refined over as these 122 devices have gone out. He's developed a very tidy installation, mounting it to the side of the chamber wall. So you can see the battery and the telemetry device here, transducer on the pipe. So hydraulically, we're monitoring after the last non-return valve, and actually in this case we can show the pressure transducer just after the last isolation valve in the dry well. We see the static head from the high point, the pump delivery pressure. And in terms of failure modes that are visible in the data, you can see quite a lot. So when the pumps are running, we see the delivery pressure. If the pumps are performing differently, we might see the delivery pressure alternating between the two pumps. If they're running in a duty standby mode, you'll see a good pump, then a bad pump, so the pressure will go up and down depending on which pump. That kind of behavior is very obvious in the data. So a poor performing pump could be a blocked suction on one pump, a worn pump, or it could be a passing non-return valve on the other pump causing some recirculation. We can spot passing NRVs, so if when the pumps are off, the static head seen at this monitoring point isn't constant, but it droops down over the course of the 15 or so minutes between pump runs. It's possibly the main draining down from the top down, and a reduction in that static head. We can see drive faults, so the pumps are starting and then stopping very quickly, and that's very visible in this pressure data. If the non-return valves after the pumps stop aren't closing properly, or they're very slow to close and some reverse flow builds up, we can see very large water hammers caused in the mains caused from the non-return valve slam, and again that's very visible at the pressure monitoring point. A burst main, say happening sort of close-ish to the pump station, would result in a much less restrictive pipeline and a change in the delivery pressure, and would look different to a pump failure because it happens for both pumps or for all pumps. And we can also see sort of air valve closure events as well, so slamming of air valves, and sometimes in steady state data some evidence of air valve closure and change in state on the rising main. Okay. In terms of the data that we get, this is an example of some of the summary data. You can see the dark blue lines are the min and max pressure. The blockiness is the 1 minute periods, and the mean value in blue is the mean value for the 1 minute period. So you can see when you get this static head, this site has a very stable static head at about 2.9 bar. And then when the pumps are running, we get a very stable delivery pressure up in this sort of 4.3 bar range. You'll notice that the min and max lines, when the pumps are running and when the pumps are off, are very close together. So we have a low range. That's worth holding in your mind for later on. And when we have these transitions between off and on, we can see we've got a large range in values seen. You'll see some detailed high sample rate data later on, which will fill out what's actually happening in there. But you've got a surge going up to the max value and then a stabilization at the delivery pressure. And then when the pumps stop, obviously you're trying to decelerate a column of fluid very quickly. Most of the systems we've been looking at so far have been star delta drives, so quite aggressive control on the pumps. You'll see a sudden drop in pressure and a decaying oscillation, which falls within this sort of min-max envelope we've got shown here in the data. So there's quite a lot to see in the data. So as Lorenzo was saying from the outset, a key objective of the monitoring system was the detection of a burst rising main. And quite early on one of the first systems we were looking at, we had this example of a burst captured. We've actually got two monitors shown here. We've got one at the pump station in red, and then one further along at an air valve chamber in blue. So if you ignore the blue data, which is unfortunately sitting in the front, and look at the red data, there's about 30 days of data here. So it's lots of starts and stops all bunched up together. The dark red is the mean pressure, and the lighter red in the background is the min and max. So you can see the sort of range of pressures seen on the main. But the most important thing is that this delivery pressure starts to drop off for the burst. And if we look in a bit more detail at that failure, you can start to see the individual pump cycles popping out on this plot. So the colours have changed. We're now blue at the pump station. The dark blue is the mean pressure, and the light blue is the excursions on the starts and stops. You can see that just before the failure and this drop in delivery pressure over 2 or 3 hours was a much higher delivery pressure, which was from 2 pumps running simultaneously. And if you look in even more detail still, this is 3 pump cycles. You can start to see some of the high sample rate data overlaid on top here within the min-max envelope. This is on the left-hand plot, the first pump run is the one with the much higher delivery pressure. And what happened is the 2 pumps stopped at the same time and caused a very big negative pressure, so much lower pressures than we'd normally see after a stop. So the fluid's still moving away from the pump station. When the pumps stop, it causes a suction at the pump station. 1 bar on this y-axis is atmospheric. It's an absolute transducer. So anything under that is a vacuum in the pipe. So on this pump stop, we caused a 0.3, 0.2 bar vacuum in the pipe immediately after the stop, which could have been worse further away from the pump station. If the elevation goes up slightly, you'd have seen a bigger depression. So after this event, having captured this event, we thought, well, we've got our first ideas for an algorithm for spotting bursts here. We're going to look for a low delivery pressure. If you look at, we went and visited Lorenzo actually after this failure and looked at the sections of pipeline that had been removed. And once we'd linked the two together, it was the story started to pop out about what had happened. And what we think had happened is that the pipeline, in this case a 600mm ductile iron pipe, had a erosion of the invert at the bottom of the pipe. So you can see the wall thinning in the right-hand image. It already failed, already cracked along its length, and that crack had been plugged with rag plugs in the pipeline. And the negative pressure from the 2 pumps stopping at the same time, we believe, dislodged the rag plug. And then over the following sort of 2 or 3 hours, the positive pressures pushed the rest of it out. So we saw this sort of the sudden stop causing a dislodging of the rag plug. Sorry, I'm just going to ask for background noise to calm at my end. Guys, can you be quiet, please? Sorry, I've got a whole family of kids behind the door. So you can look at some pretty simple models to look at why the delivery pressure would reduce when you have a failure on a pipeline. So the pump curve is shown here in red. which is the output pressure from the pump in terms of meters. And then on the x-axis here, we've got the flow rate from the pump in liters a second. So when there's no flow from the pump, as in it's fully restricted on the output, it will deliver 105 meters head, and as the flow rate goes up, the delivery pressure drops. Conversely, the pipeline has a positive response in terms of the head required for a certain flow rate. So if you want to increase the flow rate, you have to increase the head. What you have is an equilibrium point. So once the pumps have started, the fluid's being accelerated in the pipeline, you reach this equilibrium point where the green dot is, which is the delivery pressure for the pump station. So we can see the predicted delivery pressure for this system is maybe 55 meters head, and the predicted delivery flow would be something like 55 liters a second. If we look at a failed system where there's a burst in the pipeline, you would expect the pipeline response to change. So the pipeline is now less restrictive, and the interaction point between the pump curve and the pipe response changes, and we'll see a reduction in the delivery pressure and an increase in the flow rate. And this is what we're looking for in the burst alarm. So if we return to the example data, and what we're saying we want is a means to spot where this mean value is marked up. We want to be able to pull those points out from the data and see when they've reduced. And the key thing, as I was saying earlier on about the stabilized delivery pressure and the stabilized static head, is the value range. So derived from 128 samples a second, the range is very small. So if we were to, for each minute of data, look at the range of values, if it's small, then we can run a test on the data to see where the mean value sits. The best way to do that is with a zone plot we found. So if you take each minute of data and plot it as a cross on this diagram, on the x-axis is the mean pressure in bar, this time, sorry, swapping around between meters and bar, and on the y-axis is the range of pressure seen in that minute. You start to see in this zone 10, the second zone across on the left, on the bottom. This is a cluster of points around 3 bar for the static head. I think I can maybe point on here. There we go. There we go. So this is the static head zone. So when the pumps are off, you see data in this sort of area. And when the pumps are running, the mean pressure goes up to about 4.5 bar. So you'll see a cluster of points here. And the transitions between off through to on are a big transient with a large range of values, and they go up through these 3 zones in the top. So by looking at which zones the points appear in, we can start to build up a picture for how the system is operating and whether there's a fault. So low delivery pressure, for example, would result in all of the running points dropping into this zone 20. A low static head, so for example, the main is draining down and we're seeing this reduction in static head, we'd start to see a small tail heading into zone 00 down here. If you've got 2 pumps running, we'll see operation in the higher end of this zone 30. And if you've got a blockage, we might start to see things creeping into zone 40 over here. It's actually quite hard to spot blockages. And big transients might start to place points much higher up. In here, we've got big slams on stops from the non-return valve. Just turn this pointer off. Okay. So one of the things we started looking at was histograms for these zones. So if you label each of the zones with a text-based label of what you think it is, you can start to look at, well, it's not really a histogram, it's a counter of how many minutes are seen in each state. You can see for each day you've got 1440 minutes in a day. You can mark up how many minutes are spent in each state. We haven't actually used this yet, but we felt this was quite a good way of visualizing how a pump station was performing. And when you start to see the undesirable states creep in, like low delivery pressure, you know that faults are starting to occur. If you see all of your delivery pressures as low delivery pressures, you might conclude it was a burst, and that's the basis for our existing burst alarm. This next slide just shows a different burst. Actually, we've caught probably 10, 15 bursts, I think. I'll confirm a number with Lorenzo, but this is another example of a burst, and we've got some different plotting algorithms here, but it's the same sort of visualization method. We've got the zone plot on the bottom, which is the timeless plot of mean pressure against range, and on the top is the time series data and the summary data. And you can see we've highlighted in dark blue on the bottom the points in the burst zone, and in the top plot you can see the reduced delivery pressure from the burst zone. So just by counting the points here, we can raise a burst alarm. So in terms of configuring this burst alarm, we need to know what the expected delivery pressure is and what the expected static head is. We found two ways of doing that. The first way is empirical, so you install your tapping, you put the device out, you look at what your data, you examine your data, look at the delivery pressure and static head. If they look stable and you're seeing no drain down, no big slams from the non-return valve, and the delivery pressures are nice and stable and the pumps are performing the same, your conclusion from just looking at the data is the system is probably performing okay, especially if you know that you've got no leaks and you've walked the line maybe. Then you can simply set upper and lower limits for delivery pressure and static head based on what you've observed in the data. But another method, and a slightly more robust method, is to predict what the delivery pressure and static head should be. So we take the pump curve, we take the long section, get the static head from the long section, calculate the flow head loss from the length of the pipe and the diameter, and predict from the system curve what the delivery pressure and static head should be. And if you take this more analytical approach, you have the added benefit of spotting pre-existing faults. So if you've already got a leak on the main and the delivery pressure isn't where it should be, or the pumps are worn, you can start to spot a system that isn't performing as it should be, even though from the shape of the data it may look okay. Just a sort of small section on air valves and air in mains. So with trapped air in mains, it's generally undesirable to have big pockets of air in rising mains. One of the main problems is it normally contains corrosive gases, so H2S, which can age your pipeline prematurely. It can it generally occurs on the downhill sections of the main. So in this case, you're looking at this section here is where the air pockets would start to build up. So if you didn't have the air valve, they'd be in there. It means that you get a gravity flow downwards. You lose the benefit of the sort of suction head from that. So your delivery or the apparent head of the main increases. So you have to pump harder. So you're less efficient pumping down the main. It's a restriction. It can cause reflections in transient waves. So when you get a pump stop, we get these rings which reflect from the end of the main normally, but they'll reflect from a different point. That's not always a problem, but it's quite a useful way of diagnosing if you've got a reflection point that's not the end of the main. The other problem with them is that you can get water hammer when the air is expelled. So if you imagine you've got a pocket of air at this high point and an air relief valve is working, you start the pumps, you push the air out by pushing flow in from the pump station side. You've got a static column of water to the right. Once all the air is gone, you've got water moving at maybe 1 or 2 meters a second towards a static column of fluid. So when the air valve closes, these two columns crash, and you can create very large water hammer events. And often they're not visible at the pump station. So if you're monitoring at the pump station, water hammer events from air valve closures partway along aren't always visible. They won't pass through other air pockets, for example. So in a few instances, we've also looked at monitoring partway along the main, and we have found air valve events that weren't visible at the pump station. But for most mains, just a single monitor at the pump station seems to work. We've been continuing, as Lorenzo said, we've been continuing to evolve and develop the products. We're actually moving away from the green telemetry boxes with the display and moving to a simpler variant. It's got no screen. So I've got a window popped up. It's got no screen, so we're trying to reduce the cost a bit, but it's got quite a few improvements. So it's got a 4G modem in it. It's got a brand new processor, a new firmware on the device, a much better operating system that gives us a lot of ability to do more analytics on the device if we want to in the future. And we've got a new communications method with radar, which is much more reliable. And that combined with the 4G actually gives us, as long as you've got even a marginal signal, cellular signal, we get almost complete data transfer, so we don't get any gaps now. So it's quite an improvement. So that's called PM1. In terms of the data coming from these devices, all of it ends up in Radar, which is our cloud platform. So Anglian Water have accounts. As soon as you bought one device, you get a managerial account on Radar, and you can then create sub-accounts for as many people as you want. So the information is available across an organization. And from Radar, you can do device configuration, you can view all the data, set up alarms, we can set up API access so that you can pull data out automatically. You can get alerts for not only sort of primary alerts about functions of assets, like the burst alarm in this instance, but you can also get sort of status alerts for devices. So the batteries are running out, or it's gone offline, or anything else that's going to mean your monitoring isn't occurring effectively. Then you can be alerted to it, so you can take a proactive action. Here we've got just an example of the burst alarm for rising mains. So ultimately we send emails out to customers automatically on when a burst is detected. It's got about a 6-hour response time, so we're analysing 6-hour blocks of summary data to look for failures. And at the moment that's quite a big improvement on where the response time is for bursts. But we think we've got ways to improve this still. The existing burst algorithm is all right, I'd say. It picks up probably 70% of bursts, but it also misses some, and it has some false positives. But the algorithm was developed off the back of 1 or 2 bursts and has been run then for a year. And as Lorenzo was saying, we've got a wealth of data now from 120 devices out. And we've actually got a program of work going on now to take the next step with the algorithm and massively improve its accuracy. So we're aiming to deliver not only a much more accurate burst algorithm, but secondary alarms for other performance indicators on the main, whether it's blocked pumps or passing non-return valves, that sort of thing. Okay, and just to reiterate, when you're looking at data on Radar, it's possible to use sort of manual data analysis of the data in Radar to infer all sorts of other failures, and we're looking to automate these in this new revised alarm. Okay, I think I've spoken for enough. I'll pass back over to Lorenzo, and he's got some great case studies with examples from their work.
Thanks, Ben. No one can hear me. Just put it in the chat, and I'll bring the microphone closer to my mouth. Right, yeah. So I was going to go through some case studies that we've seen since we've put some monitors on, just covering the sections around why we wanted to do this monitoring, to give you a bit of a sort of show you some of the benefits that we've seen. So burst alert. So on this particular site, we were having frequent burst events, and the way that we would pick them up is when we would get a call in from our customers. We put the monitoring onto site, and you can see this is quite a good illustration. In the top right hand corner, we've got our burst settings, which then give us the zones around where we're targeting to see that data, and then once the data falls within that zone, we get an alert. And you can see that in the illustration on the left there. The pump station is running around. The pump station is running around 4 bar there, and you can see quite a significant drop. It falls within that burst state zone, and then within that zone there, the alarm comes into our operational control center, and you can see over a short period of time we've managed to find the burst, we've isolated it, and we then return the rising main back to normal operational state. And the key thing with this was that our, and you can see from the bottom, that our repair bill previously, because we didn't know it had burst, was around 25k. But because we knew it had burst and we could get there in a fast and controlled manner, and we could plan it in as well, we significantly reduced that repair bill and the cleanup. And I think the most important thing in terms of our key sort of ODI performance measures is the impact on the environment was severely reduced. So because we knew it happened, and with this technology, we're not saying that we're with this sort of success criteria we're going to reduce burst, but if we can get there quickly enough, we know that we can reduce the impact of the pollution and save our environment. So that was a really nice sort of illustration of how the alert works, and some of the benefits that we've seen. And this is, like I say, and Ben was saying, it's only one of a number of scenarios. On top of that, another thing that we've been looking at as well is operational efficiency. So the acceleration of exploitation has really happened by putting loads of sensors out there and just seeing loads of data. So we have an optimization analyst within the team who looks at this data on a daily basis and sets the burst alerts up. And while we were setting burst alerts up, we were coming across different data sets. We wanted to know what them shapes, what that data meant. And this was one scenario. And with what you can see here on the top right, every time the pump stopped, there would be a drain down, a significant drain down back in the well. And what that meant was that the NRV was stuck. It was stuck in an open position, so they're being closed when the pump was off. And what that would do is then the rising main would drain back into the wet well, which, as you all are aware, that's not efficient. That's not how a non-return valve should work. And it poses several other risks in terms of surge and emptying the rising main, in terms of gases, etc. Introduced in terms of rotting the rising main. So what we were doing there is every time the pump stopped, the water would come back into the wet well, and we were basically just pumping water around in a circle. Not that severe, but you can see there that the stops and the starts of the rising main are more in the top one. So a job was raised, a technician went out to site, inspected the non-return valve, found that they were blocked full of rag, unblocked the non-return valves, and then you can see in the bottom picture we've maintained a static pressure of where we should be. Instead of the top one where every time the pump stopped it drains down. And we ran some quick analysis on this and how much energy it's saving, and we can see on this site they're fairly small pumps, but just with that intervention, and it was only a couple of hours that the engineer was on site for to derag and find the root cause of the problem, we're saving £1,100 a year on energy. And now this is what we're working on Syrinix to automate this as well. So we've got 122 sites. I want you to tell me how my pumps are performing. So all my non-return performance. So you can tell me whether they are open or they're closed. So we can then start to grab some of that operational benefit in terms of energy. Another good one as well, and where we've really expanded on this, is we've worked with some of our modelling partners in terms of exploring this data further with Atkins, and then within our own internal modelling team around exploiting some of that surge data. yeah, and with sound problematic. I'm reading something. It might be in my headphones. Sorry, okay. So yeah, so we've been using modeling data as well to exploit the surge analysis. So we've been using tools such as Wanda, which is a surge analysis tool, and we've been taking a load of static information from the pumping station, so the elevation of the rising main, the pump curves, what air valves we've got, etc. And we've been inputting that into a model, and then we've gone, right, this is how a rising main should operate. Well, this is how this rising main should operate based on the static data. And then we've compared it with the live data we've been getting from the Syrinix model. And that's been really, really powerful in terms of understanding, especially for sites that are bursting frequently, how we should be operating them. And this is a really good case study on this site. And this site was bursting quite frequently. You can see on the left here, every time the pump stopped, the surge pressure will go up to around 20 bar every time the pump stopped, and then you'll get the ringing off on the rising main, and then which is a significant surge event. The surge shouldn't be that high if it could be managed differently. So what we've done on this site, we installed variable speed drives, and then we inputted into the model what was the most effective time, stop time or ramp down time, to get the best transient for the rising main. So on this one here, we had a 25-second ramp down time, and you can see the on the right hand side slide there, the transient is significantly reduced from where it used to be around 20 bar every time the pump was stopped. It's now around about 8 bar. And the key thing with this, and the key thing with the rising mains, is how they're around the negative pressure. So on the left hand side there, you can see where the pump stops, it goes right down to sort of atmospheric pressure. Where on the right hand side there, it goes down to around 3.5 bar, around 4.5 bar, which is a significant difference. And a lot of what I'm learning with rising mains is the pressure change instantaneously has a big effect on how the rising main performs and it acts in terms of burst conditions. And we've seen a massive reduction in burst frequencies. So, as a big tick, we could actually pick up the bursts, but now we're going into the zone now where we're actually increasing our asset life. So we're not having to invest in new big rising mains, which cause a lot of disruption to the community and are labour intensive in terms of design and construction. There are small solutions out there which can increase the life of our rising main significantly by understanding how they're performing, by using modelling data and powerful modelling surge analysis tools. But then more importantly is having the live data on site. So in effect, mimicking your digital twin and then going, right, let's mess around with the digital twin to see how we can make that rising main perform exactly how it should be to increase the asset life. And we're doing a hell of a lot of work on this. And we're investing heavily in this area because we feel this is a strategy that's going to increase the life of our assets in terms of having to replace them and defer that capital. And this is just another sort of slide on that sort of case study. So this is from the surge analysis tool, and this is what's really powerful with it. So we hadn't made any changes, but this would show us what would change. So on the left-hand slide here, you've got the green line, which is your rising main. So this is your elevation profile going to your discharge point. And then you've got your min and max pressures. And this is based on a pump shutdown. So this would show you how much of your rising main will be subjected to negative pressures when the pumps stop. So as you can see, pretty much the whole rising main to the peak would be in continuous negative pressures, which is not how a rising main should operate, and that's a significant risk in terms of its bursting. But once we put the modifications into the model, so we put the slower ramp down time on the pump, you can see that most of the rising main is at positive pressure, which is exactly where it should be. So you're not turning your rising main into a vacuum main, you're turning into a positive pressure main, how it should be operating. And this is really powerful in terms of giving a confidence to operational staff around the solutions, because some of these solutions have not been implemented before around VSDs on pumping stations and the way they've been controlled. We've had VSDs and pumps for years, but the way that we're controlling them is very, very specific for the purpose that we're trying to serve, which is reduce the burst frequency. And this data is really, really powerful in terms of showing operational staff and giving them the confidence to go in for that solution. And we're seeing burst frequencies drastically reduce from our baselines by introducing this type of analysis. I'm really sorry about the sound. Yeah, like Oliver said, he's going to record us. So, and if there's any questions afterwards, please feel free to get in touch. Just going to touch on benefits. So while we're accepting at the beginning that we are not going to be able to reduce bursts when we first met this technology or started to use this technology, we wanted to reduce the impact of when a burst did happen, and we succeeded in that on a number of cases. And Ben's sort of highlighted as well. We are now at a learning stage, and I've never seen a project like this in the way that we have learned and explored. You know, we've put loads of these sensors out, we learnt loads. We have missed some bursts, and now we're investing in improving that with Syrinix. So we are now building a more robust algorithm which can actually pick up on events that we have missed with the current algorithm. So that's going to increase our visibility of bursts around the business. We are again working with Syrinix. Now we know what a non-return valve failure looks like. We can now start to automate that approach. We can put, I don't know, say 50 sites into a list of hierarchy of what sites that are failing, because we're constantly monitoring them in terms of their non-return valve failure, and then we can prioritize that potentially on energy spend, for example. So we could go and send contractors or our own technicians out to go and have a look and unblock NRVs, replace NRVs, to then reduce our carbon footprint, reduce our overall electricity consumption, and protect our rising mains as well, because the non-return valves serve a purpose in terms of how they support the surge on the rising main. We're doing our best bit around extended asset life, so working with Atkins, surge modelling companies to increase the life of our assets by understanding them more and inputting current modern day technologies to control our pumps better. And I'm not. This is not any fancy technology. Some of it may be a case of just making the pump run for longer, which is, that's not heavy investment. Some of it may be how we change and we operate on non-return valves. Yeah, these are not massive changes, but there are massive changes to the overall asset life, which I feel a lot in the past has been ignored. We just expect we maintain a lot around the pumping station, the air valves, the rising main. It's a significant cost to the business, and monitoring this has really changed the way that we operate and supported us against the harsh determination that we're going through at the moment in terms of the strategy that we're imposing. While when we do know that, we're able to defer capital spend. So if we do need to replace rising mains, and we will have to, this strategy is not going to say you'll never have to replace rising main again. The key thing about it is we will replace rising mains that need replacing, that definitely can't have mitigation put in place, that need replacing. So we focus our money on the right areas. And as a better understanding of system performance, we can start to pick up on pumps that we're wearing. We can then start to introduce maintenance standards, etc., and target on them assets. Again, just to sort of quickly elaborate on this, we're improving our burst alert. We're going to start automating maintenance alerts around non-return valves. We've started to integrate this data into our OT platform. So we've integrated the data from Radar's platform around the burst alert, and it goes straight into our telemetry system now, which is a massive win-win for us. So that's an area we're exploring more. And we're continuing to innovate with Syrinix at the moment with pressure monitoring data. We're seeing benefits on a daily basis, and the business are really engaged, especially our operational teams are really engaged with the data, and they're seeing the benefits. Ben, I'll hand over.
Okay. Well, thank you very much, Lorenzo. I think there's some excellent examples there, and sort of extending where we're going with the data. So I've just got a few points to summarise, really. I think we've covered the development of the monitor and the primary functions, We've looked at the analysis of the data and how we can generate automated alarms and other sort of insight by manual analysis of the data. Looked at where we want to go next with the burst algorithm. We've looked at the data from, we've got more than 100 systems deployed, and the data from those and how that's being used to refine the techniques. And some great case studies. From our point of view, I think there are other avenues to explore too. We've done a lot of work in potable water looking at shape recognition of transient events, and I think there's a lot of mileage in looking at the transient response of the pipeline and how it changes over time. And we've got some tools that we can map across to start to look at that. We're very interested in taking SCADA feeds in from customers. If we were able to get an hourly feed it's just a report of starts and stops for a pump station, we can use that in the burst analysis to further refine it. We think we can get that data from our transducer as well, actually. We're always looking for improved tools on radar in terms of analysis tools. We think we've got adding some of these prediction tools for how the rising main should be performing into radar is certainly being considered too. So hopefully, I think this, from my point of view, it's demonstrated some really interesting work going on between Anglian and Syrinix. And I must say it's been a real pleasure to work with Lorenzo, and we've had a very open and very good communication with them about all of the technical details here that's really made it work. So yeah, it's been really great for us too. Right, well, thank you very much. Oliver, I'll hand back over to you, I guess, for some questions.
And you may. Thank you, Ben. And certainly, I'll reiterate Anna's point, a very interesting webinar. We'll move across to the discussion screen, and if you've got any questions, please type them into the chat window, and I'll ask Ben and Lorenzo. From Gonzalo, please could you explain the benefits of using an external pressure transducer?
Yes, so the first one is if you've got a deep chamber, you want your pressure monitoring point perhaps at the bottom of a 5 or 10 meter chamber. You want the telemetry device at the top where the cellular signal is strong. That's the first reason. And the second reason is you don't want a long line to the transducer because you get a head loss and you can get clogging and blocking of that line. So you want the face of the transducer right on the pipe. And the other one is that we wanted to split the system from an energy point of view. We don't have ATEX approvals yet, but by splitting the system, putting the high energy cellular stuff in a package that can be positioned outside of the explosive environment, it means we've only really got to worry about the transducer when we come to do ATEX.
There's a question for Adi. I understand each time you change accessory, you need a year to learn the model. Question mark, e.g. the air valve used was wrong for water hammer. So if you change its behaviour, it's totally different?
I'm not sure about the year learning. The change is very quick. We can, if we put a device on a rising main, we can look at the performance within a day or two. We'll get enough cycling to see what's going on. Not sure why it would what would take a year. Anything from you, Lorenzo? It's
a question from Anna Boyles. What roughly would be the initial outlay per installed unit and any associated costs for telemetry? I presume there'd be a economy of scale, yeah, to be honest. But
we need Mark Hendy for this. Mark, you are unmuting. Mark is our UK Business Development Director. Mark, are you there?
Yeah, sorry. So in terms of the data and the radar licensing that gives you your sort of access to the platform, typically a SIM card's costing you about £120 a year to send up to 50 megabytes of data each month. And on top of that, you have a radar fee of £275. And the advantage of joining now is that the hardware is being cost optimized. So it really depends on whether you want to use rechargeable batteries. Obviously, Anglian have taken the approach to go mains powered with the hardware, which reduces the cost again. But ballpark, if you're thinking around £1,800 for a unit with rechargeable battery.
So a question from Martin Bragg, which has possibly just been partly answered. How often you change your battery units?
So
replacing batteries. So
the rechargeable battery, we've seen the good performing ones lasting just over a year with the rechargeable pack. But we have, as Mark's saying, we've got alkali packs available, various battery options. It's an external pack, so you can do that, or you can have mains power if you'd prefer. So the default for all of these systems was great. Lorenzo?
Yeah, no, in terms of answering how often we're changing the battery units, so it's all dependable on signal strength on the cellular network. I think the longest I've ever seen a battery out there is around 9-10 months. We're normally going around every 6 to 7 months to change a battery on a rising main. But we are trying to optimize that. So we're trying to optimize it via changing antennas and potentially looking at how we pull our data back. So, for example, what I mean by that is the less critical sites, potentially bringing our data back once a day is sufficient enough, which will then, again, increase the battery.
So I don't know if there's any more questions, but for those of you who are still on the call, as I said, it's been on YouTube in the next few days. If you're not a member of the WIPAC group on LinkedIn, do go to Water Industry Process Automation Control on LinkedIn and join. And there's a monthly magazine that comes out which features last month, which featured this case study from Syrinix. So if there's any more questions, Gonzalo was saying, what about using these units in DMZ?
That district metering zones, I think that's what it means. I think that applies.
The more from water. Yeah. So we do. So we use these on drinking water. We also use we have a different variant that has exactly the same data feeds with an internal pressure transducer, which we use on drinking water, on potable water, and that's where all of this work started. Was looking at water hammer and transient events in drinking water. So in drinking water, actually, there's a lot more analysis you can do that doesn't map across the rising mains. So you can look at wave propagation, you can triangulate bursts to understand where they've come from. You can look for large industrial customers, all sorts of things. So there's a question here.
Another question.
How effective is the pressure sensor in detecting bursts after the highest elevation point in the main? From my point, I'll let Lorenzo speak as well, but from our point of view, obviously you're looking at this flow model. The further along the main the burst is, the smaller the change to the delivery pressure will be. So it's more effective earlier in the main. But if you're right at the other end, it's not as effective. Lorenzo, do you have any more on that?
It's a really, really good question. It's something we're learning more and more about. I think there's only been, so we've got 122 units out there. There's only been a couple of sites where we've seen, we've had a burst and we haven't picked up nothing. We've not seen any change on the data. So it's a rare occurrence, and the reason why it's a rare occurrence is because predominantly most of the bursts are on the first section of the rising main. That's where the highest pressures are seen. That's where the highest negative pressures are seen. But rising mains where you're, let's say, 6-7 kilometers long, potentially in the future we may have to monitor across the rising main on strategic points to pick up on bursts. But if you've got short rising mains, which a lot of our rising mains with Anglian are, so when I mean short, you're looking at 3 to 4 kilometers short, then the majority of the time we're picking up the change in performance and lead to a burst alert raise. But it's a very, very good question. Something we're learning more and more as we're going through this.
Okay. I can see Adie's explained his question a little more. So when the comments about the taking a year to analyse data from the sites and sort of conclude what bursts look like was in terms of designing the burst algorithm. In terms of analysing a single site, you can do that very quickly. You know, the transient data is available for the response of the system within a few minutes. Normally, the device is being deployed. But, you know, with a day's worth of data, you've certainly got a good feeling for how a particular rising main is performing. If you're doing transient analysis, it might take you a week to put the model together, or a few days to put the model together. And then compare the output of the model to the rising main to look at, first of all, to get correlation with the current performance, and then to explore the effect that any changes might have, like changing an air valve. The reference to 1 year was about our learning about what you can see in rising mains generally from the pressure data. It's taken us a year and 120 systems to start to get a really good feel for what can be achieved.
So we've accelerated a program of transient reports now. That's what we call them, and we can produce them pretty quickly now. We've got standardized processes, so standardized data that we need to grab from site. We've got people that are more familiar with building these models, and I think like the great thing about having the models is the ability to input different types of air valves to then give different effects in terms of pressure. And what we're trying to avoid most of the time, well, all the time really, is negative pressures, which cause a significant impact on performance, especially PVC pipes, which we have a lot of PVC pipes.
And if not, we'll leave it at that. Thank you all for coming to this WIPAC webinar. Keep an eye out on LinkedIn to see about the next one. Question from Wayne: do you find that your model outputs fits your measurements closely?
Yes, in terms of the outcomes. Yes. On some sites, not every site. When I've seen the presentations that the modelers have presented to us, there are cases where they've uncalibrated the model, so they put everything in that we've given them, so where air valves are, length of rising main, etc. They've turned it on, they've shut a pump down, and you can see that the transient from the logger matches exactly with the model, which is great. It shows exactly how it's performing. There are cases where they have to calibrate the model, so they have to put in different types of information that wasn't presented to start off with. So they have to put a different air valve that's not working, or the air valves that are put on the rising main, turn them all off because it looks like they're not working at all, and then that gives them a different transient. Most of the time, from a modelling perspective, the modelers try their very best to calibrate it to what the site's telling them. But there have been cases where they've just calibrated, they've turned on the rising main on a model, and it's just matched exactly with what the Syrinix data is telling us. That's very good. In terms of the outcomes from the recommendations, we have seen a significant reduction in burst events. So once we do complete the model, the rising mains are not bursting what they used to. And we're keeping a very close eye.
So unless that's it, looks like there's no more questions. If there are any more, I'll stop the recording now. If anyone wants to ask any questions, I'm sure Ben and Lorenzo will be around. Thank you all very much for coming, and hopefully see you at the next webinar.